Hello everyone, and welcome back to a new episode of SHENZHEN I. It's been a few days since I had a chance to record, so I don't recall exactly if we were in the middle of anything. I remember we finished the last project we were on, right? We're not in the middle of an actual level. This was the coin thing, that was fun. I think there's, if we wanted to, plenty of opportunity to revisit previous problems and find a way to solve them better with new tools. But I'm not particularly keen to do that at the moment. I'd like to get on to a new puzzle. So what's this one about? Product is a haunted doll. Can you keep a secret? Doing some research on the internet, it seems that if a doll is a haunted doll, it brings way more interest. Okay. Haunted dolls that get caught on a live stream are almost guaranteed to go viral, so what if we took some of the dolls from a factory and put some parts in them to haunt them? Then gave them along with normal dolls. Oh my god. Does not seem like a good business plan. Are you serious right now? Okay. Found some appropriate sound effects. Sinister giggle and blood-curdling cry. Some unmarked chips from a long while ago. Who knows why they were originally made. Whoa, that's... I don't know if we want to put some unmarked chips into dolls and just give them out without telling people, but... Okay, well, let's make a haunted doll. So, what is a haunted doll? Okay, first, what's our board look like? Mid-sized, I guess. This is an unknown chip of some description. Maybe it's in the specs, maybe not. Random is a simple input. Is that this? I guess it must be. Connected to a random number generator. Speaker is a simple output, here, connected to a miniature self-amplified audio speaker. When a value of 1 is generated, play Sinister Giggle. When a value of 2 is generated, play Blood-Curdling Cry. Look in the supplemental data section for the audio data that Carl found for those sound effects. Okay, so we'll get to that in a minute, but first I want to just test what this guy does. It's a simple input, so actually we can just do that, alright? And so is that how you use it? No. Which, okay, there we go. Apparently it's this one down here. Oh, there's a little arrow. Got it. Okay. And so all it does is it generates allegedly random numbers in the range, it looks like, of 0 to 100. Maybe it can't go all the way down to 0. Maybe it can't go all the way up to 100. Maybe that's just a coincidence of the data we were looking at. Who knows? But that's good enough to a first approximation. Alright, so now we gotta go look at the specs. I assume we're being asked to basically play a series, not play, yes, play, but I'm trying to think of a way that doesn't frame it in terms of sound, something that's not self-defined, or like a circular definition. I'm back. I had to step away for a minute, but as I recall, well, actually, I don't know exactly where I cut the video because I haven't cut it yet, but at any rate, we had just figured out how this thing works, and we were about to go see if in the specs, what these audio files we need to play are. So, giggling was in there or something? Sinister Giggle. Ah, the creepy sound effects page. Okay. So we wanted to play these two. Okay. And it's just like a... Wow, that's a little scary. Very military. So we want to play a sequence of numbers like one time unit at a time is the main interesting part of this puzzle, I presume. Figuring out how to play these, well, not play, how to write the logic for actually outputting these numbers in a like, I mean, so you could write this in like the most obvious way imaginable if you had enough bytes, right? You could just say, you know, move 100 to P1, sleep 1. Move 80 to P1, sleep 1. Move 41 to P1, sleep 1. But like, there are 13 of different volumes we have to play, and that's costing us 2 instructions, I should say, each. So it's like 26 instructions to play one of the 2 sound files we need to play. So that kind of seems like a non-starter. So we'll get back to what those numbers actually are when we figure out like the right way to do this dang thing. We can't actually get that down there. I guess here I'll do. So the most obvious and straightforward thing that I can see is like to have a. And the thing is, this is not a finished implementation plan. This is just like an approach that seems like it could have some merit. Is to do something like this, and you know, maybe, I don't know, wire up this guy to here or something like so, and connect these guys with XBus, and just have this be like, you know, sleep until there's some stuff on, what is it, X0, move X0 to P1, and like that's it, right? So this guy would be a controller for this thing, basically, while this guy decides whether it's time to send a sound file, and if so, then it just like goes through the instructions of like, it does those 26 steps of sending this over here. Now, of course, the problem is we don't have space for 26 steps. We have 14, and we need more than 26 anyway. So it was like, oh, wait, that's not really gonna work. So, what do we do? Okay, do we have any new parts that would be promising here? What is this about? This looks pretty good. It's got numbers on it and stuff, right? So what's 200p-14 all about? Read-only memory. Oh, how useful. Okay. Read-only memory offers embedded system engineers the ability to access up to 14. How convenient, we need 13. Factory-programmed memory cells for a wide range of applications. With auto-increment, you won't have to waste registers keeping track of addresses even. Oh, very funny. Okay. Alright, so there's 14 cells. And 2 pointer thingies into it. So the diagram looks cool, but I want to start with this usage list. All memory cell values are set in advance by the engineer. That's me. All memory pointers initialize to point at 0. Memory pointers can be read over XBus with A0 and A1. That's these two. Those are the memory pointers. So you can read the pointer to see what address you're at, I guess. Memory values referenced by pointers can be read over XBus with the data pins D1 and D0. After reading from a data pin, the corresponding pointer will increment automatically. Can you write to the memory pointers at all? Don't know. Oh, I see. And they've got this diagram here saying that, like, if you want to, you can read them all in a single time unit, of course. Right. We don't want to at the moment, but oh, look, an example circuit is a data packet generator. So this is a lot like what we need to do, except we want to do it not all in a single time unit, basically. So it's reading whatever input it's got, trigger, and if it, yeah, okay. And then otherwise it moves 0 to x3. Okay, good. So you can do that. You can write the memory pointer as well as read it. That's not a thing that was mentioned in usage, but it looks like we can do it. And then we just copy from its data pin to our output, and then jump back to the loop until. So that reads the entire thing. We're going to need to be a little more careful because the lengths of our things are different, right? This one is 5 and 13. This is 5, 10. Oh, they're both 13. How convenient for us. All right. Okay, well, I'm glad I didn't spend too much time figuring out how to solve this problem with the tools we had before, because the new tool that we have been given drastically simplifies the problem. And indeed, it's hard. I could imagine maybe someone smart could figure out a way to squeeze this all, like, to squeeze enough data onto this board without using this new chip, maybe. But it would be pretty hard, and with it, it shouldn't be too bad. So we're going to need 2 of these, one for each what am I even, hello? One for each sound file that we need to play. I'm not sure exactly how the controller on those is going to work. We can maybe just have one of these guys do all of the everything. Maybe, like, this seems like the absolute minimum amount of hardware we would need to solve the problem, right? And it might be that we need more. It seems to me at a first guess that the did the volume just get higher for some reason? Am I crazy? The song seems real loud all of a sudden. I don't know. Okay, I'll just talk louder. Well, okay, so let's say we couldn't do it. So this here has exactly enough I/O pins to do everything we need to do, right? I'm not, like, obviously this is maybe not the best way to wire things, but you could imagine a setup somewhat like this. No, stop. I mean, you guys see what I'm getting at, where this writes to the output and also connects like this, basically, right? We read the input, see if we should trigger a sound file. If so, we start reading from one of these, the appropriate one of these guys, and writing to the output. So the question is just if we have enough code space in here. I don't know the answer to that. But it gets a if, like, let's imagine this isn't enough. how do we fix it exactly? Well, we could add one of these guys to read each sound thing, or maybe just one of them, and assume that this guy's smart enough to handle the other. But like, this guy can't write to the output, so he would have to like send his results back here, I guess. I don't know, it seems a little complicated, so it would be nice if we could do it just like this. Although I'm not very fond of the layout of this chip, but you guys get the idea. So first of all, let's lay things out a bit nicer, shall we? Like so. Is that good enough? Oh yeah, of course, because I forgot which needs to go where. So we can actually just, we don't need to do any crossovers if we write it, if we make it this way, right? We could just go like this. And actually it's probably a little nicer to go this way. And then we can move this here. Maybe scoot it over just because why not? Does it? Okay, well, fine. We'll move it down then. And put this guy at a convenient location here. Okay, that's a much better layout than what I did a minute ago. Very professional. I would put this on my resume for a hiring company. Hardware company, I should say. And obviously, we can fill in these numbers later. They're easy. But what would the loop for this look like? It would basically be like test equal P0, right? P0 to 1, and well, we can't necessarily just read, because we're gonna need some loops like in the It would be nice, wouldn't it, if we could just add like one more level of indirection here and put oh, we have a register. But I was gonna say, and put like an actual address, like use a pointer basically. If we could like use a pointer to indicate which of these XBus things we should actually be reading, wouldn't it? But it's not so easy to do. I think we can fit this all into the one chip though. I'm not sure exactly how, but it should be doable. Yeah. So I think what we're gonna do is use dat or ac. Yeah. Okay. Use dat or ac or something to store which of these things we're playing sound from, basically. Okay. And then in the loop, we'll check that to decide which one to read from, rather than... So the other way you could do it is to have two separate loops, one for reading from this guy and one for reading from this guy. But that would use up a lot more space and it would make our conditionals a little weirder. So I think what we're going to do is... Yeah. So we're going to say if it's equal to 1, then we will just move a 1 into dat. Okay. Otherwise, we will test whether it's equal to 2. That's the other thing we're supposed to do, 1 or 2? Yes, okay. And if so, move 2 into dat. Now, there's obviously some duplication here. But the problem is, you can't just do the obvious thing of move P1 into DAT. Although, well, okay, so first of all, you can't just do the obvious thing because we want to be able to use DAT to save, well, right, because we, yeah, I'd like to, I'm just trying to think, like, I think it probably is easier to just do that, isn't it? Yeah. So let's just do the obvious thing there then, and just move. Wait. Yeah. Move P0 into DAT, and then we'll test eq. Now, of course, at first this looks like, why do we even move it into DAT? We could have tested it if it were, I don't know. But we're only going to actually do this read on time cycles where we're not in the middle of playing a file. When we are in the middle of playing a file, we're going to need to be able to refer to DAT as what file we were in the middle of playing. So okay, so we're going to test eq. The problem is it's a little bit awkward to test, is it 1 or 2, right? So I think maybe it was better the way we had it before. But we can save an instruction, I believe, by here saying move P0 into DAT. So first we see, is it 1? And then, if not, we check whether it was 2. If either one of those succeeded, we move P0 into DAT. So we can now assert that DAT is either 0 or 1 or 2, right? So what that means is, I think here we can say, if it was not 1 or 2, we could actually write a 0 to it now, and I'm not sure whether we need to. I don't think we do. We can sort of handle that later. So let's just call this jump to done. And down here we will say done sleep 1. Okay. That's sort of the structure. And now the question is, can we fit the logic for reading a thing in here at all? So I think what we're going to do is, at this stage, we know, play. We know we're sort of in a state where we want to play a sound. And let's also do this. How do keyboards work? Oh, I can't hit enter because I've already... Gross. Alright, whatever. Move 0. Oh, shoot. Alright. So now we kind of have to do this test again. Test eq P0. Oh, interesting. We kind of... It's a little bit awkward because we need to reset both of the registers to 0 before we start the loop, the address register. Not both. Whichever address register... Oh. Let's just reset them both. That's easier than resetting just one of them. So we'll just move 0 into x1 and move 0 into x3. That's initializing our loop. We're really starting to run out of space now. So I hope we can squeeze everything that we need into these last few lines. So this is how we prepare to read from the beginning of one of these memory chips. So what we're going to do is say, at the beginning of this loop, we're going to check which sound file we're playing. Test equal dat of, no commas, what am I thinking? 1. If it was 1, then we'll say that that's this sound file. Move. I was thinking that we would read from the memory, the address register line thing here to decide when we're done playing the song. But that involves like a branch to decide which of these two things to read from, basically, right? It's like 2 instructions. And it's a little awkward, isn't it? So maybe the thing to do is, before we start, to move 13 into ACK to say this is how many sounds are left to play. We're really getting shorter and shorter on space though, so we may have to go back and figure out how to optimize something out. Okay, so if it was equal to 1, then we will just move. Okay, this is, yeah, we don't have much left to do actually. Move x0 into p1. Otherwise, move x2 into p1. And in fact, oops, no, I keep that one. We don't even need these anymore. X3 is not connected. What's wrong with, who cares? Am I reading X3? Yes. Oh, right. I'm not reading it, but I am writing it. Very fine, okay. I was thinking since we figured out how to not bother reading from these registers, I could disconnect them, but that is not the case. Okay, and then what we're gonna do is sub 1. And then if so obviously I want to go back to the play loop most of the time here, right? I'm just having a little bit of trouble articulating how to actually fit the sleep instructions in at the right place. So like, okay, let's say, I guess, we're definitely gonna need to sleep 1 here, it seems. This is the most straightforward approach, maybe not the best. And we may have to go back and choose the best instead. Yeah, since we're now like out of instructions, we can't squeeze in what we need here. Okay. So we can, I think we can get these redundant sleep ones fixed a bit. So let's sub 1, and so right now we need to basically say sleep 1 So now we're sort of jumping. Let's see. We need to squeeze another test in here. Test equal ACK with. We don't want to test whether it's okay. So here's the trick that I'm trying to apply. We'll see if it can be applied successfully in the space that we have. Well, my idea is to make this sleep 1 line get reused both for the normal state of operation and for the actually outputting sound state. We're jumping here to done. We're jumping over this looping part, but we're going to try to reuse the sleep expression. And so to do that, I'm going to put my comparison before the sleep. And I'm just not sure exactly how it is, exactly what comparison. I need to compare to 0 or to 1 or to -1 or something. But I need to do it in such a state that, or in such a way, I should say, that minus causes nothing to happen, and plus causes me to do a thing. So what I really need to do is test greater than. So if ACK is greater than 0, then we will jump back to play. But not right away. We'll do it after this. Right? So the idea is, in the case that we decided not to play a sound file, we'll jump down to done, and we'll sleep for 1, and we'll get to this jump play, but we will still be in minus mode from having done these tests up here, right? Yeah. Okay, sure. So at first glance, this appears to have all of the necessary steps, right? We test whether it's 1 or 2, and if so, we save that into DAT so that we can continue to remember which one it is. We initialize each of the memory chips to start reading from the beginning, even though we'll actually only read from 1. And we set our counter at 13, and then we go into this loop where we check which chip to read from and move the corresponding chip to the chip's data value to the output. Then we subtract 1 from our accumulator and test whether we're out of bytes. Then we sleep for 1 and either jump back to the beginning of the play loop if there were bytes left, or don't do that, i.e. fall back to the top and start looking for new inputs. So let's just try a simple test here where we just write, well, let's make this 50 and 100 so it's a little clearer to know what's going on, and then these are 14, right? Yeah, 14. So then in here we'll write a 25, and here a 75. And so what's wrong with the speaker? It's supposed to output 50 otherwise? What? Oh no! 1 extra byte that I need. I need 1 more instruction to squeeze that 50 in. Right? It has to go right at the top, here. Okay, well, let's see if we can handle what I thought the requirements were. This is a case of not reading carefully. I thought that this line was, like, I don't know. Sometimes it seems like I've just seen horizontal, like, I didn't see the line at all because they've got this, like, horizontal line that's, like, where 50 is, right? Ugh. Okay, but now let's say value, was it 1? Yes. Move a thing to DAT. Now we initialize both of these things to 0. We move 13 to our accumulator. Was DAT 1? Yes.
So we play a 50. We sub 1, getting us down to 12. We say, was it 0? Or was it positive? Alright, well, sleep. And then, yes, it was positive, go back to playing. So next we write 100. And we write 0 a bunch of times. And now we should write the 25 and not the 75 is the idea. Did we succeed in writing the 25? I don't see it exactly. Okay. I'm a little confused because act says 1. Oh yeah, so it jumped to... How did we end up not... Oh, wait, I see. Yes, we wrote the 25, and then when it came time to write the 75, we decided not to. Okay, so this solves what I thought the problem was, but not what it actually was, because we're just the tiniest bit short. We need space for one more instruction if we want to fit it all on this one chip, which is at the very top. When we're not playing sound, we need to output a 50. And if I can't do that, it's going to cost me probably one of these guys to do extra I/O with these guys. Right, basically I would remove the data connections from here to these guys, connect this up to them instead, and connect this guy up to here saying, hey, give me some sounds to play. But I'd rather not do that if I can find a way to squeeze out one more instruction. We already did one trick. So, what if we tried reading the data registers instead? Yeah, that might be good enough. So we could take out this 13 move here, and instead replace it with each of these two instructions. I was thinking it would be kind of hard because I would have to just figure out which register's address thing to check. But I can actually just check both using an OR, right? If either one of them is pointed at 14, then don't jump back. I think that's okay. So let's try it. We're going to remove this. We're going to remove these. And we need to do a test in such a way that plus means to... We want a minus result if either of these address registers is equal to 14. Okay. So that means I want to test something like, is it less than 4? So test less than x1 14. So if that's true, wait a minute. Ugh. I'm now pretty sure that we actually have found a way to squeeze in that extra thing. So let's go ahead and write it now. move 50 to P1. But okay, so actually, I think we can save just the tiniest bit of power by putting it here, basically. Only at the end of a time cycle, when we're not already outputting something else, do we fall back to actually outputting 50. It would be just as correct up here, but it would waste one cycle in the case when like when a thing actually comes in. Oh wait, no, that's real wrong. This way, when a sound ends, the very last thing... Oh no, it would be fine because it's after the sleep. Okay, I think we're all right. I don't know if that's really improving anything. Anyway, so we're saying test less than 14. So if that was true, then we need to do another test because we need to check the other one. Test less than... Oops. X3 and 14. Now, if either of these tests gave us a minus result, then we're not going to jump back to play. And that will be correct because whatever thing we were reading from became 14. All right, so let's see if we can get the same behavior we got before, but with 50s. Oh, I see. Right, we have to write that before we sleep. All right, so whatever little micro optimization I might have been getting there is not one that I can get. So let's put, stop, what, paste. Move 50 to P1. So maybe we're wasting cycles on occasion here, I don't know. But hopefully that fixes correctness behavior. Okay, great. So now step up to here. We write a 50, but momentarily we'll be replacing it with something else. So now we're going to test... Actually, we'll be replacing it with a 50, so... Okay, but we do all this stuff. We initialize them, we check which file we're playing, and we read the first thing out of it, which is a 50 as it happens. Then we say, has this one caused us to wait. Yeah, I think that's right. Has this one caused us to have we gotten to the end of the file assuming we were reading this one? The answer is no. Have we gotten to the end of the file of this file? The answer is still no. So we sleep for 1, and since the answer to both of those was no, we jump back to the play loop and continue playing. So let's see, look at this number go up. We're just continuing to read out of this. Okay. We write out the last thing we actually wanted to write, the 25. We sleep for 1. Jump back to the play. Wait a minute. Alright, we played the 75, which we didn't intend to play, so we've made a mistake there. Yeah, this loop is never ending. Alright, well that's not very good. So I think what we actually need is to turn this into this. No. How do I implement a friggin' OR? I know I've done it before. So we're first testing, is x1 less than 14? Why is that not working? I still think that this plus was right, and so I must be missing something else silly. Let's see how we actually... Alright, so which... We're now getting ready to read the second to last thing, I guess. Okay. We just read the second to last thing that we wanted to read. Nothing interesting happened. So now we're about to read the last value we want to read. We've read it, and now x1 is... Oh! Wait a minute. This is 0, which means this is 6. Yes, that's 13. I was working in a 1-based in my brain here, even though I obviously knew that was incorrect because I started with putting zeros here. But that was a while ago, and so I just sort of like forgot about it. That should be better. So now we're going to read that last thing and say, is it less than 13? No. Therefore, don't jump back to play, but rather go back to our normal mode of operation. Okay. So now we have some, what do they call it? Data entry to do, right? 100. So which one are we doing on a 1? Is it Sinister Giggle? Yes. So 180. Good. At least enter works. 41, 14, 14. Whoops. 41, 14, 14, 41, right? Yeah. 69, 74, 54. 69, 74, 54. This is what being a programmer is like. It's not. 27, 19, 40, 75. 27. 14, 70, 95 or something? Not even. I got all the numbers right, but in totally wrong order. That is to say, I didn't get 2-digit numbers right, but I think I said all the right 1-digit numbers. The digits of them. So 19, 40, 75 is what we have left. Also, I wrote that wrong anyway. 27. 54, 27. 19, 40, 75. 19, 40, 75. I'll put a 0 there. Okay, so that's one of them. Let's confirm that this correctly handles writing Sinister Giggle. We did it. We wrote the right thing, and we're continuing to write the correct thing. And now, look at that, a 50. Cool. So we hopefully just have to input the data for the second song. Not song, sound. 16, 36, 42. 16, 36, 42. 14, 10, 58, 100. 14, 10, 58, 100. 76, 26, 28. Did I put that in right? No, I didn't. It should be 28. Wait. What am I even doing? 76, 26, 28. Okay, I just misremembered it. 70, 80, 42. 70, 80, 42. Alright, let's see how it goes. Looks great. Wait, why did it stop? I don't understand. Everything looked good to me. What went wrong? Each of these is exactly as expected. No red lines anywhere that I can see. Oh, I bet I typed in one of the numbers wrong somewhere. And it's just like, it's off by not enough for me to easily see it. Okay. I guess we're gonna have to do some proofreading. Gross. So here I see 180, 41. Yes. 14, 14, 41. Yes. 68, 74, 54. Ah, 69. 69, 74, 54.
A+ if you caught that one while I was entering it.
Last up, 27, 19, 40, 75. Yeah, that looks good. All right, try again. Okay, there we go.
So I don't know what's going to happen if anyone ever... Well, I do know what's going to happen if someone pushes both buttons at the same time or something, you know. Or if a 1 comes in while we're in the middle of...
Cool. Okay, so it looks like most people... Well, maybe about half of the people figured out how to do it with the minimum amount of hardware, as we did. And the other half spent more somehow. I'm surprised it's as high as half. I thought that what I did was like hard and clever, but I guess there's a lot of clever people playing this game, so there you go. And in terms of power usage, we look like we're about in the middle. I'm not sure. 334. Like, I'm not sure which of these two bars we're in. It looks like we're in this one, actually. So the mode was like more people figured out how to do it with less power here. But we're at, I think, basically the median, more or less. All right, cool. So returned email. Let's get our congratulations. It worked, kind of. Someone posted their haunted doll being haunted. It was starting to gain attention, but very soon afterwards they opened up the doll and found the mechanism, so it was solved pretty quickly. But they still don't know where it came from, and I believe that ghost electronics have a potentially very bright future in the marketplace. We could even build them during ghost shifts at our assembly lines. I'll research the possibilities. I forbid you from doing anything further relating to ghost electronics. Alright.
So that was a good one. We learned a new piece. We had a reasonable algorithm, and we had... I feel like we squeezed at least 2... I know we squeezed at least 2 instructions, maybe 3, out of like the obvious way that it occurred to me to implement it. So overall, it was a good program. There you go. Enjoyed the puzzle. Hope you guys did too. Thanks for watching, and I'll see you next time.